Hi, I'm Mike Kowalenko, and in today's webinar, I'm going to discuss data fusion and analytics and how we can use some of the new techniques and technology in data analytics to improve our quality stance as well as demonstrate process control and improve productivity in the pharmaceutical manufacturing arena. Now, as we think about data fusion and all that, what are our goals that we're trying to achieve in the pharmaceutical operations? That is, we want to optimize our supply chains, we want to optimize our facility utilization, and we want to do things right the first time. So the question comes up, can we have it all? And basically what I mean by this is it possible for us to do a good job and release product on time with no rejections or deviations? Or if we have deviations, have effective CAPA that actually addresses the root cause? And then can we, as a quality organization, assure that when we are manufacturing that the requirements are met and that we have a sufficient overview of what's happening on the shop floor as well as what's happened in the past? And I think that's a very important point, because that's what allows us to do the practice of management review. That is, can we go in and look at past production and current production and draw the right warranted conclusions about operating in a state of control? Can we have effective failure investigations? And that's linked to an effective CAPA. And can we make sure that we don't manufacture at risk? What we don't want to do is have everything in a constant state of flux. From a manufacturing point of view, we want to consistently understand how long it takes to produce a product and to release a product. Unfortunately, when there are deviations or failure investigations, these are open-ended exercises where we have to solve the mystery of whether or not the product's safety or efficacy has been compromised by the deviation. This in turn can lead to lots of investigations and data scouring and all of that in order to produce a decent failure investigation, one that can be scientifically justified and is backed by data. Now, along with talking about data fusion and analytics, we have to think about digital transformation, because this is something a lot of the pharma organizations have said they've embarked on. Well, in order to do a digital transformation, you have to have the same things in place that you have for failure investigation. That is, you have to apply critical thinking and problem solving and figure out what you want to do in this digital transformation. What are you trying to achieve? And in order for it to work, there can be no silos of data. Everything has to be integrated. We can't have this command and control structure where everyone says, well, if I have knowledge or I have data, I have power, and I'm not going to share that. That just doesn't work if you're trying to implement a data-driven culture, which is the goal of most digital transformations. The data has to be readily available. It has to be in near real time or real time in order for you to make decisions. And along with that, there's got to be a method, or there's got to be the systems in place that lets us look at fusing the different types of data and information that we have on hand together to get a holistic view of what's happening in the organization. Now, before I get into some of the analytics we may deploy in a production facility, let's talk a little bit. Let's go back to basics and talk about the attributes of data. Well, first off, remember, data isn't knowledge. Knowledge is created when you take that data and apply it to a problem or come up with a statement about that can be supported by that data. All right, these are where facts come in, okay? We're not talking about assertions, and assertions are our opinions about things. Facts are if I look at a production line and I look at let's say in biomanufacturing, and I'm looking at cell line productivity, there is a number for that. I don't say, oh, it feels good. There actually is a number that I'm looking for with regard to grams per liter of productivity. So again, understand, data is just data. We have to turn it into something of meaning, and that's where the critical thinking and problem solving comes in. Now, in order to do that and extract the facts that we need in order to make our decision, we look at all types of data. So let's talk about the types of data a bit. Quantitative versus qualitative. Well, quantitative, almost everyone is familiar with. Those are the things you add, subtract, multiply, and divide. It becomes very easy to think about it in the sense of some of the statistical programs that you often see. It could be SAS or R or Python in what it does in SciPy. So there are a whole number of ways of looking at things quantitatively. Qualitative data are things that are descriptive. That is, I can say I like something or I don't like something. The problem with that is what I like and what you like could be two different things. So you have to figure out a way to take a qualitative, an observation model, and turn it into something that's semi-quantitative or quantitative. And with that, there's a whole separate lecture I could talk about on qualitative data and how you're about doing that. I think the biggest thing to understand is that with qualitative data, we have to think about and well define the system that we're measuring, and those measurements can be observations. I could say the equipment looks clean by visual examination, but I can quantitate how clean it is by doing swabs and then determining whether or not there's evidence of a contaminant, let's say a protein residue left in there. So qualitatively, I could say, yes, it looks clean, but quantitatively, I may say that there's a certain amount of residual left in that tank. Now, the other type of differentiation I want to make is between structured and unstructured data. And in most organizations, you're going to have a mix of those. Structured data is the data that goes into a database. And that database could be your LIMS system, it could be your ERP system, it could be your deviation system or document tracking system for things. Those are all systems that store information. Now, the content within them could vary a bit. Every time that you have a structured data source, it generally relies on a relational database, and you've probably heard of those. Those are things like SQL or Oracle or Microsoft has them. Again, relational databases you could think of as large Excel tables, though I hate using that analogy. And I look at information row by row, and each column describes a certain attribute of the data. Unstructured data, on the other hand, are text, videos, audio, such as this presentation, and what you have there is just an amalgam of words. But we can use current processes in compute, natural language processing, to extract valuable information from those text. And that text could be contained in a field within a database. And when you think about it, unstructured information is often associated with qualitative models. So the two of them go together. That's not to say you can't use the techniques of natural language processing to isolate facts, and those facts can then be quantified. So there's a slight difference there. The other thing that's important to remember is that with structured data, you have to predetermine everything that's going to go into that database. Databases don't like to be changed, and you see that all the time when you try to, you get the wrong address on your mail and you try to get it changed. Getting someone in the company that sent the mail to change the database can often be a difficult task. Again, it's just the nature of wanting to keep that data in a nice, orderly fashion and not change it frequently. So there are the other drawback to structured data is you generally have to know the questions you're going to ask before you put in the structure or the table that's going to store that information. And that often leads to places where we're not collecting the right information, or we need to collect more information. Data stores are, where do I put that type of information? So again, we've talked about the relational database as something that we view as a table structure with columns and rows. And we can have that in all sorts of forms that, from a IT infrastructure point of view, makes it easy to move data around. The problem in the long run, though, is as we do more analytics and we have to move more and more data, there's a cost to that in regard to performance. And if you're working in a cloud environment, it can increase your cost of operations. The format of the data is also important. And while we may have multiple database systems, such as our LIMS system with its overlying architecture that you can get from, let's say, Thermo Fisher or a number of other HP and other companies that produce these packages of a front end where you enter data or collect information and store it, they all are based on relational databases. Now, when I talked about the rows and columns, even though I can look at an ERP system table and let's say a LIMS table, and they both have the same column for a given attribute, let's say they are going to tell me the number of pounds of sodium bicarbonate I have on hand. One of them may give that measurement in integers and the other may give it in float. This is incompatible with compute systems that are looking to bring those two things together. So oftentimes we're left with the task of trying to harmonize these things. And many times that's left to the database administrator and leads to, again, a delay in you being able to get that information and use it in an application. We do have systems now, one from Nova Systems, that you can control all of that and you can make those sorts of changes in a really easy fashion. And it allows you to get to decisions quicker. Now, the final thing is speed. How quickly is the data generated? We have SCADA systems that measure things in real time and can take process flow information and we can do analytics on it immediately. There's absolutely no problem with that. We could take the information from a LIMS system and incorporate that as well. Any place where we have data popping up on the screen, we can pull it in and do the calculation. Now, the type of question you're asking may or may not require that degree of speed. You have to think back to the problem you're trying to solve. Is it important for you to make a decision right at that moment on a process? Well, in that case, speed is important with the analytic. If I'm looking at reviewing a whole series of development documents, it may not come up immediately, but I do want an answer within a very short time frame, a couple minutes, couple seconds actually. I don't want to go reading through all of those documents myself and try to come up with the pieces or the facts or pieces of information I need for my decision. So again, I can really speed up my process of fact extraction through the use of some of these new analytics. And you know, I've used the term advanced analytics, and now I think it's important for me to define what I'm talking about when we start thinking about advanced analytics. So we're all on the same page, a bit of level setting. And when I refer to advanced analytics, what I'm talking about are things such as machine learning and neural networks. And now I'm going to talk in generalities about what these things do. Well, the first is they can classify data based on known attributes. That is, we can look at it and say, well, if it contains X, Y, and Z, label it A. But if it contains A, B, and C, label it Z. In these cases, and what we're talking about here is a type of supervised learning where we're telling the machine how to sort things. The algorithms can go through and group information for us. And it does that based, as I said, on the attributes. Now, this can also occur without us telling the machine what the groups are based on the algorithm that I use, I can say to the machine, okay, sort this into different groups based on these features. Which groups had, and by that, what we're doing is we're saying this group has a common set of features and another group has a common set of features, and that's all we're pointing out. Remember, the machine doesn't understand context, and the only thing it's doing is saying there is a correlation with these data in that they all occur together. It doesn't make a value judgment. It doesn't say that that is the cause of something. That the interpreter, the human, has to look at and say, does this make sense? This is where the subject matter expert can look at a machine's output and say, yeah, it's okay, but there's no way to explain some of these groupings from a scientific basis. And that's very important to understand, that the machines don't have the ability to look at context. All right. They can, if I have enough data, come develop predictive models, because I can say, look, in the past 5 years, I've measured these different parameters, and I know that if I see this feature drift, my product is going to fail specifications. So based on that information, I can develop an algorithm that says, look at factors A, B, and C, and if you see C drift, raise a flag. All right? These are normal regression analyses that have been around forever. All right? Bayes' theory, Bayes lived in the 1700s. So why are we talking about all of this now? And the reason for that is compute got really cheap. That is, we have processors that have a tremendous degree of capability. And what we're doing is we're allowing ourselves now to do brute force mathematics on these large data sets. I've got the compute, and I've got storage that's cheap, and I can exchange data easily. So now it's just a matter of running the numbers through the system and seeing what we can use and how we want to use it. But I'm going to emphasize again the fact that you don't want to go into a data analytics problem without understanding the question you're asking. Machines don't like ambiguity. Neither do data scientists, and it's really hard to make a decision on ambiguous data. Know the question you're asking. I mentioned a number of different algorithms that can show up in these big data or data advanced analytics. Most of them can be grouped into these different categories of linear regression. That is, I have a constant stream of data and I can determine what the next value is going to be based on the past. I talked a little bit about supervised and unsupervised machine learning algorithms. Supervised are ones where you tell it what's good and you tell the machine what's bad, what the attributes of good are and what the attributes of bad are. And when I talk about attributes, what I'm talking about is the way you're characterizing the universe, and that universe is where you're performing the analytic. So all of those columns represent different attributes or features in a table of the question you're trying to answer. Supervised, you provide that input. Unsupervised, the machine is sorting. Feature reduction is to say, well, if I have a large number of attributes or columns in my table, is there a way for me to determine which of these is meaningful or not? And there are a number of algorithms that do that. You may have heard of PCA or k-means. And in fact, what we're doing there is we're looking to see what the impact is of each one of those attributes on the outcome. If I see no change in the feature numbers or what I'm measuring in that column, but yet the product changes, then I know that feature doesn't actually help me, and I can eliminate it. The machine can just do it faster and with more columns. Sorting is where the machine really stands out, because what it's going to do now, it's going to start grouping elements together, different units together based on their attributes. Oftentimes you hear these types of algorithms referred to as ensembles or random forest, decision trees, those sorts of things. It's a type of sorting that's aimed at isolating a unit, the thing, that universe you're measuring, based on unique attributes. Classification, on the other hand, often comes in when I'm doing natural language processing on unstructured data. Can I read through that data and find different ways of saying, let's say it was a good review or a bad review? Or if I'm talking about something that pertains to us in the pharma industry, can I look at a deviation and classify that deviation using a machine? Can I train the machine using a supervised model on past deviations where they're labeled as being like human error or equipment failure or environmental monitoring excursion, and have the machine read through those and develop a set of analytics based on those features, on the features in those systems, and be able to predict what class it's in. And that, again, is something that can be very helpful in pre-screening or filtering information for you as you're doing things like failure investigations. The case I just spoke about with failure investigations makes use of natural language processing, which is a way for us using compute to reduce text to various forms that we can look for patterns in. And what we're trying to do there is to associate those patterns with a given outcome or with a given label. And I'll go into that probably in a separate lecture altogether. Needless to say, it's now possible, and we at Novi Systems have developed a really neat system that allows you to use natural language processing in a very straightforward manner. It's not it's not necessary that you have advanced training in data science or programming in order to implement any of these features now. We've got ways of doing that where if you're interested and you want to bring the data together, you can. Now, what I've done is to talk, we've talked about these different methods, and let's look at where I could apply some of those analytics in my process. Well, as I said, we've got, process performance, what's happening over time, and trending, equipment changes. Could be a couple things, all right? So process performance and real-time stuff, we're talking about regression analysis. Process change could be something where all of a sudden I'm monitoring something. Let's say I changed a probe, and I want to make sure that I continue to get the same types of measurements over and over again. Or I can look and see if there are new observations associated with performance based on equipment change. Are things now cleaner or not clean? Those sorts of things. When we're talking about checking training effectiveness, that's generally a classification system using natural language processing. Do I know how the people have been trained, and can I look through the documentation using NLP and determine whether or not, by changing something such as an SOP because of a deviation, I in fact have accomplished my goal? Deviations themselves, those investigations make use of all of these tools. And what that does is it really speeds up the process of making a decision, because you can have all of that information readily available now, provided it's all fused or integrated. The other cases are pretty straightforward, and you can understand where we can apply these models. I think the big thing to remember here is that if I can form that good question and I'm clear and objective about it, there's a good chance I have a way of looking at both quantitative and qualitative data in order to make a decision. Well, we talk about what the machines are doing, and we speak about artificial intelligence and the fact that, we have certain people who believe artificial intelligence and machines will take over the world. And I actually don't ascribe to that school of thought. Machines can only do what they're told. all right, they're good at what I call puzzles. And puzzles are where there's a boundary. You have to operate within a boundary or there are rules. This is why machines are really, really good at games, right? Games have a set boundary defined by rules. And so what the machine can do is figure out different strategies a lot quicker than you, because strategies in a game are a sort activity. And remember, that's what machines are good at. What can't the machine do? It can't deal with ambiguity. Let's talk about natural language processing. If I'm talking about tolerance, and my training, I'm an immunologist by training, what that means is that tolerance for me is whether or not a graft is going to survive in the host. If I was a sociologist, tolerance would have a totally different meaning. So a machine, if you tell it to look for tolerance, it's going to find tolerance, but it doesn't understand the context in which it was used. However, if I look at the terms around tolerance, I may be able to develop a pattern that says if I see this word with that word and another word, I can classify it as being associated with immunology or in the same pattern with sociology. And these are some of the techniques we use in natural language processing to help us extract information from unstructured or text. Now, humans, on the other hand, handle ambiguity really well. I mean, if I make the comment, giants beat socks with bats, we pretty much know I'm talking about baseball. Now, if you don't come from the U.S. or a country that uses baseball, you might think I'm talking about a sadistic fairy tale. What I'm talking about here, though, is our brain has the ability to make those logic leaps and associations. Machines can't do that. Humans can also understand context. Machines have to be told. Humans get really bored doing simple tasks, and chances are that leads to error. So we have the machines do all that stuff. And again, humans are good at mysteries. That is, we don't really know the end, and we don't know all the boundaries. And that's something that we look at and can solve puzzles. Now, in pharma, lot release is a combination of puzzles and mysteries. So we may have certain things that fall out of specification or weren't quite done by license. Does that mean it affected the safety, efficacy, purity, or potency? Well, that the human has to determine by looking at all of those facts that the machine has brought forward. So what I'm really talking about here now is intelligence augmentation, not artificial intelligence, but the ability of the machine to help us with the decision by allowing us to explore the facts that it's isolated. It's a very important concept when we start thinking about how to use machines to help us solve our problems. Now I want to come back to, again, this view of our data and the fact that we have all these structured databases collecting information, and we need to get that information together for the release process. Unfortunately, almost every place I know, all of these things are isolated. That is, they're kept in different systems. Although they're all databases, there may be issues with the data type, as I said earlier when we talked about floats versus integers. And what I'm trying to do is review all of this stuff. And that becomes really, really hard if I've got all of these different pieces of paper floating around everywhere, and I've got it all siloed. And I also have no way to look and see how what I'm looking at today is comparable to what I've seen in the past. Because again, of all these different searches and sorts and things like that I'd have to do in collecting information. Now, the good news is that we can integrate all of these things. We can bring it all together through the use of fusion. And what I mean by fusion is our ability to have software that allows us to perform tasks related to what the data scientist has to do for transforming data, or for what a reviewer has to do to see if things are trending and tracking properly. So let's look at fusion here. And what I've highlighted are just 4 systems. And the fact that each system is isolated, but each contains a common piece of data or a common unit or feature. And in this case, it's the batch number. And I would have to go to the SCADA system, do one thing, and go to LIMS system, do something else. Well, if you look at Fusion software, what it's going to do is it's going to take all of the data from these different systems and perform that extract, transform, load function, the thing that's the bane of every database administrator, and allow the system, all right, upon interaction with the human who fed it in, to do this transformation in a really straightforward process. And once that transformation is done, apply a whole series of analytics to it. Now, the nice thing about this is that it generates an interactive dashboard that you see as part, in this case, batch release, that allows a quality organization to look at current performance and past performance and really have all the information they need on hand in order to talk about a release decision. If I was in production, I could do the same things for my in-process controls, all of the things that I'm looking at with regard to, well, what are my flow rates, what are my seed densities, all those things, and make comparisons. And I can do it in a way that lets me mix and match. Let's say I had a good batch of material that seemed to grow extremely well. Can I look back into the media constituents from the ERP system and determine whether or not certain producers of raw materials, their raw material, even though the COA from them and another company may be the same, still provides a better response? It allows you to do those sorts of questions, and you can do it without having to deal with database administrators and all those other things, because the software handles these problems. And what it does is it extracts these tables and works with those tables in its own environment. And that, again, avoids the system for interfering with ground truth. At the same time, when it does that, we can implement all sorts of tools to assure the integrity of the data, the testing, and all of those things as they run through the system. So Fusion is a real enabler when we're talking about doing advanced analytics and trying to get the best of both worlds. And that's remember, that's really what we want, right? We want to be able to release quickly, but we also want to demonstrate that we're operating in control. These are the sorts of systems that allow us to do that. Now, the next place I'm going to go is failure investigations, because we see this time and time again when the FDA issues out their summary of different inspections. Many times, it has to do with ineffective failure investigations. Well, the problem generally comes back to what I talked about at the very beginning. What's the ideal thing? Can we do things in a timely manner? Well, production wants you to release something, or the product may be in short supply. You want to get it out there. And you start rushing through the investigations. You don't do a thorough enough job. You don't clearly state what the problem is. You don't collect all the data and look at it historically and do the appropriate statistics to determine whether or not there can be any correlations between a change and, you know, what happened in change control or equipment change or media change, things like that. And the reason for that is it's so difficult to get the information together in a timely fashion. Well, using Fusion, as I just mentioned, allows us to significantly increase the speed in which we can collect that information and do the assessment. Now we don't have this time constraint per se, because remember, the machine is going out and it can sort much faster than you, and it can take in more data than you, and it can perform the tasks of determining what's relevant or not relevant if you give it some information. So now we can really focus on writing and performing a good failure investigation that's scientifically based and uses the data that you extracted to state clearly your assertion about the product, right? You've collected the facts. Now you're going to make that assertion about whether or not the product's safety, efficacy, potency, purity has been affected. Right? having this time now and using this information results in a better state of control. The other thing that it does is it allows us to look at performance over time and readily determine whether or not things are trending in a good direction or there's opportunities for improvement. What we don't want to do, and what we're trying to stop, is what I call the deviation death spiral. We get a little bit of information and we draw some, we bring in a subject matter expert, we look at these things, and all of a sudden we find something else. We've got to collect more data. We go through that same ABC loop again, over and over and over again, reviewing the license, and finally being able to make the release decision. The real problem here is in C, all right? We have a difficult time in these organizations bringing all the data together. And again, this is where Fusion can overcome this problem and stop the death spiral. The last thing we want is to have it take a year to resolve a deviation on a product that's only got a 2-year expiry. There's a lot to be said about that. First off, timeliness. Why did it take a year? And secondly, does the marketing group really want something that has that short an expiry date on it? So I'm going to go back and say these advanced analytic techniques, and more importantly, our ability to monitor them in near real time, allows us to avoid these types of death spirals and demonstrate a better sense of control. Now, in machine learning and failure investigations, in this example, what I'm demonstrating is that we can take the text from different development reports, and that's what's represented by those Adobe files, and use natural language processing to extract the pieces of information we need to deal with a failure. That is, can we go to a development report and show what the impact is of, let's say the error is the oxygen sparging didn't occur as per SOP, and find in a development report where oxygen concentrations were varied and its impact on product quality. Because the data is now integrated and we're using machines to sort and find this stuff, it occurs within seconds. And the software we have now is able to read anything that you have in electronic format and convert it into something that it can use in this NLP process. And that's what you see on the left. It's just a flow diagram that shows you what the algorithm is doing to try to classify the piece of information that you've given it. Now, another way that we can use big data and these advanced analytics is in something such as looking at chromatographs. Oftentimes people have to set the gates and do these observations and try to disambiguate peaks. Well, software can do that now. I mean, that's why we have all these visual analyses tools. That's why Tesla is making a self-driving car, right? Because it can look at an image and classify the image. Well, we could do the same thing with a chromatogram. We can have the system look at it and model it based on past controls and past performance and come up with a system that can automatically label, and that's what you're seeing here in this chromatogram, where the peaks are, and then do the calculations about area under the curve or whatever else you want to do in order to quantitate those peaks. Now, the flow diagram at the right actually demonstrates a couple things. The first is the fact that the machine is doing all of the peak analysis and collecting the data. The second shows how the machine in the background can look at data, historical data, and compare it to what's happening now and determine if there's process drift. At the same time, the system can take that data and lock it down and know the number of times analyses have been done so that we can overcome data integrity issues. Again, these are all things that we can build into the system now that improve its robustness, improves its compliance, and provides us with an opportunity to clearly demonstrate control in this environment. Now, In this final example, what I'm doing is I'm showing you how I can use natural language processing to determine if my CAPA is effective. I can look for certain terms and for patterns of those terms in the deviations across my organization and see whether or not I'm getting a pattern evolving. Now I can go the next step too, and I can take external data. I can go to the FDA website and get all of their reports and compare their reports to what I'm seeing on my site and determine, well, does this look like something that they've been interested in? Am I doing the right things? All of that stuff. So there's a lot of applications here where you could take information that you're generating internally from documentation, such as your deviation system, where you're documenting, the deviation and the cause and the CAPAs, as well as monitoring the effectiveness. Let's say, for example, I have an SOP at 2 sites, and the 2 sites perform the same thing. The SOPs are slightly different. The one at one site results in more deviations due to operator error than the SOP at the other site. Natural language processing allows me to compare those 2 things and determine what the differences are that I could implement. At the same time, natural language processing can go in and look at deviations that have occurred since the SOP was revised to see whether or not they've occurred again and whether or not that was effective. All of this happens in near real time. This doesn't require people running around and chasing down records. They're all built into the system. So we have many, many opportunities here to get to what I'd say our desired state is. And that is, we have integrated data. We've got data integrity built into the system. We can monitor anything with regard to what's happening now or historical. We can have the system handle compliance issues as well as generate alerts and actions, those sorts of things. And what we can do now is focus on the scientific integrity of the investigation or demonstration of process control so that we know we're operating in a state of control. And we can get to our desired state of timely product release, a good understanding, great quality management, which again is something that we see in the ICH guidelines and FDA guidelines, and they've been talking about for years. All improved time, but increased quality. Well, I'm going to leave you with, you have the data. It's time for you to turn it into knowledge. And there's systems, including the Novus Systems methods that were built specifically for this sort of thing, that you can use. And finally, I can't say enough, if you're going to embark on a digital transformation, understand the problems that you face. You have to be able to state a problem clearly. You have to remove ambiguity, or else the system is going to fail and you're going to be disappointed in the results you obtain. This is Mike Kowalenko from Novi Systems. Thanks for listening.